Hello, and welcome to Astronomy 100. In this segment, what we're going to do is discuss how astronomers determine the sizes of the stars. Now, when it comes to the concept of size, it may sound rather trivial when it comes to measuring the size of a star. Today, in the world around you, if you were to measure the size of an object, you have a variety of ways to be able to do this. Measuring tape, yardstick, you could get in your car and drive a distance to measure distance. But when it comes to the stars, there are a couple of difficulties that go with measuring their sizes. So let's go to our first picture and I'll show you what I mean. When it comes to measuring the sizes of a star, one of the problems is that the star itself is producing an awful lot of light. And the distances to the stars are tremendous. It's often very difficult to try to get people to realize just how far away the stars actually are. And so what we're going to do is we're going to start with a myth that we're going to bust, something we haven't done in a while. When you look at a star in the sky, or in this case when you photograph a star, it may be hard to imagine, but you are actually not seeing the surface of the star. So this circle that you see in this photograph, or any of these circles that you see down here, that circle is not the star's surface. And the reason why it just can't be photographed is because the stars, again, are very far away and they produce a lot of light. And so when you are looking at a photograph of a star, it is just about impossible to actually see the surface of the star. An example would be if you were to find a spotlight that's shining up in the sky to advertise a new movie or a grand opening of some store, and those lights, of course, produce a lot of energy. If you were to go up to the light and try to put your head in the way to see the actual source of the light, you're just overwhelmed with light. So stars produce an enormous amount of energy, and so it makes it very difficult to actually see the surface of the star itself that's producing the energy. The other thing is that the distances are huge, and the distances between the stars are so big that even with the best telescopes on Earth, we simply cannot photograph the star itself. What you are only able to photograph is the light that is coming from the star. So let me show you an example. If we were to instead use a larger telescope, in other words, take this same picture of the same star, but use a larger telescope, well, what you would end up getting is something like this. You'll notice that this is not an improvement. Remember that the purpose of a telescope is to gather light. And so when you look at a very bright star through a telescope, it looks like an even brighter star. And so there is actually something in there. There is a star that is producing the energy, that is the light that you see in this picture, but it's buried in there somewhere. And so we don't see the surfaces of stars. There are very few exceptions to that, but 99.99999% of the stars we simply cannot see the surfaces of. They produce too much light and they're too far away. Now let me show you one exception. One exception to this seeming rule that we can't actually see the surfaces of stars would be the star Betelgeuse. Now, if you recall, Betelgeuse is one of the stars of the constellation of Orion. It is the upper shoulder of Orion. And you'll notice when you go outside to look at Betelgeuse, it has a bit of a reddish appearance to it. And what I'm going to show you is an actual photograph of the star Betelgeuse. So this is the surface of the star Betelgeuse, and you can actually see it has a certain diameter to it. And this is a photograph taken through a technique that allows us to image the surface of very few stars. Now you might be thinking, well, why are we able to do this with Betelgeuse but not other stars? The reason is that Betelgeuse is very, very large. So it is, of course, far away from us, but it is exceptionally big, and so therefore we can just barely see its surface because it is so big. To show you just how big Betelgeuse is, if we were to take the Sun out of its position in our solar system and put Betelgeuse in its place, it would fill the entire solar system out to the orbit of Jupiter. So imagine one star that is as big as all of the planets' orbits in our solar system out to Jupiter. Mercury, Venus, Earth, Mars would all be inside of it. And Betelgeuse is a type of star called a red supergiant. And later in this course, we'll talk about what that means. So Betelgeuse is one of the very rare exceptions where we actually have the ability to see the surface of the star itself. So you might be thinking, well, how big can stars actually get? And of course, how do we measure the sizes of stars? It turns out stars have a very big variety to their sizes. Some of them can be very, very small, and some of them can be just almost unimaginably large. And often people will ask, what is the biggest star known to astronomers? And you can imagine that answer is going to change over time because we will continually find bigger and bigger stars. But as of this taping, let me show you what is currently the largest known star in our universe. So let me switch to this picture here for you. Now in this illustration, this is not a photograph, but in this illustration, it might be very, very difficult to see this little yellow dot right there. This dot represents the sun. So imagine our sun shrunk down to the size of this dot. And although it's kind of unassuming, what you'll notice is this red spot has a bit of curvature to it. So what you are actually seeing is the edge of a star that is currently the biggest known star to astronomers. So let me shrink it down so you can see this star. Now I'll warn you, the sun is going to be almost impossible to see, but let's do this. So if you look very carefully, the sun is right there. There's the label, the sun. And the largest known star to astronomers is VY Canis Majoris, and it is just absolutely large, absolutely huge. It's just hard to even imagine a star that would be this big in comparison to our sun. And some of the details that go with this, if this star were placed in our solar system where the sun is, and take the sun away, put VY Canis Majoris where the sun is, it would fill our solar system out to and beyond the orbit of Saturn. So you can imagine, here is the size of Betelgeuse, here is the size of VY Canis Majoris. So stars can be very, very big, and of course they can be very small. And the sun is just actually, in reality, a fairly small star compared to how big they can get. And just let me show you some numbers. VY Canis Majoris is 2,600 times bigger than the sun. Remember, this is the symbol for the sun. R stands for radius. 2,600 times bigger, and it is producing 450,000 times the energy that the sun is. So remember again, solar luminosities, or luminosity of the sun. So this star is very big, and it's producing a lot of energy. So let's get back to the original question. If we can't see the surfaces of stars, how do we determine their sizes? We can't use a traditional means. So the way that astronomers do this is they have to use what we call a workaround. What we're going to see is that there are properties of stars related to each other. The properties are related to each other, and we can use this to figure out the size of the star. So let me show you how this works. The idea is called the temperature-radius-luminosity relationship. It has a more technical name. It is called the Stefan-Boltzmann law. But let me show you how this works. I'm going to show you a formula. And the formula says L equals 4 pi r squared sigma, this is the Greek letter sigma, sigma t to the fourth. Now let me show you what all these squigglies and numbers mean. L stands for the luminosity of the star, how much energy the star is actually producing. R stands for the radius of the star. T stands for the temperature of the star, and pi and sigma are numbers that are constants. They just never change. So what I'm going to do is show you how this big formula actually is the key to figuring out the sizes of stars. Here's how this works. So L is the luminosity of the star, R is the radius of the star, T is the temperature of the star. Now you'll notice that the R squared has a 4 pi with it, and the T has a sigma with it. Remember, there's a multiplication symbol that is to be assumed right here. So here's the idea. 4 pi r squared is actually a very standard formula from geometry. If you've ever taken a geometry class, you might have seen this before. 4 pi r squared is the formula that determines the surface area of a sphere. Now stars are spherical, so therefore we can say it's the surface area of a star. So think of it as just the surface of a spherical object, 4 pi r squared. Sigma t to the fourth is actually something we've seen before. This was called Stephan's law way back earlier in the semester, and it is defined as the energy per unit of area per second. Now, to understand what that means, let me switch to a slightly different picture. Here's the idea. The star, let's imagine we take a star and divide its surface into equal little sections. So each of these squares represents a unit of area. The total area of the sphere, each of the little ones is a unit of area. And let's imagine that if we want to know how many of these units of area altogether, well, that is just simply 4 pi r squared. So the surface area of a sphere is 4 pi r squared. Now, each part of the surface of the star has light coming through it. So if we could divide the surface of the star into this grid, each of these units of area have energy coming through just that unit of area. So think of it as this one little square has this light coming through just that square. This square has this light coming through it, and so forth. So every square has light coming through it. And so if we want to know how much total energy that the star is producing, it is the energy coming through each square per second multiplied by the total number of squares. So it is the energy per unit area per second multiplied by the total surface area of the sphere. So the idea is the energy coming through each section multiplied by the total number of sections equals the total energy of the star. So what we know is L has to equal 4 pi r squared sigma t to the fourth. It's just the physics of how this works. Now here's what we're going to do. Notice the r is inside of this formula, and we want to know the size, the radius of the star. So what we need to do is dig out the r. And if we do a little bit of math, we solve for r, here is what we get. So this is just rearranging the formula to solve for r. Yes, it looks kind of scary looking, the square root of L over 4 pi sigma t to the fourth. But what I'm going to do is make life a little easier for you, because when it comes to entry-level astronomy, we're not really interested in the very accurate calculation that would go through this. We're interested in you understanding the concept behind it. So what I'm going to do is simplify this. We're going to get rid of the square root, we're going to get rid of the 4, the pi, and the sigma, and we're going to reduce it down to this. So ultimately, the size of a star is proportional to its luminosity divided by its temperature. So let me show you two applications of this. If we know the luminosity of a star and we know its temperature, we can actually calculate its size. Here's an example. What if you have a star that is producing a lot of energy? Its luminosity is very high. Well, if the L is big, the R will also be big. This is a direct relationship. What if the same star has a surface temperature that's not very hot? So T is low. Now if T is low, R is big. This is an inverse relationship. A big L, a small t, makes a very large size. A star that is very luminous but not very hot, that is also very big, is Betelgeuse. So this is an example of a star that is very luminous, not very hot, notice it's red, and it is also very large. Let me show you one final example. What if instead we have a star that star is very hot, and we have a star that is not producing a lot of energy? Very hot, but not a lot of energy. Big T, small r, small l, small r, this makes r small. And an example of this would be a white dwarf. A white dwarf is a type of star that is very hot, not very luminous, but it is also very small. They're about the size of the Earth. And we'll learn later on in the semester, or in the session, about what white dwarf stars are. We'll leave that for a future segment. So what you can see is that when it comes to the stars themselves, we don't actually measure their sizes. What we do instead is we measure things about the star, and then we determine the size of the star based on its other properties. So stars in our universe are too far away for us to see their sizes. But because we can measure their energy, and because we can measure their temperature, and because energy and temperature and their size are related, we can determine their sizes. So in reality, we actually infer the sizes of stars rather than directly measuring them. And that's how it works. We're just about out of time, so I hope you'll join me in the next segment.